Hi class, let's try this again. I'm going to do this week's activity as a think aloud exercise and also post the solutions online, but I think this might be informative to sort of see how I think through these problems and sort of how I navigate the user interface. So first, we're looking at the assignment. We're told we need to download these pre and post test files. So I'm going to import it. We see the preview. One thing that you might need to do for reasons that I don't fully understand is you might need to disable this cache data locally option. I know some of you had trouble reading in data, and doing that seems to fix things. And we can either, again, paste this code and have all of our syntax at the very end, or we can actually run it and get roughly the same results. All right. Now, the next thing on our list is we've been instructed to find a way to show only one decimal point on the pretest score. So we are going to go to our variable viewer and modify things in that way. One thing that I do want to talk about is that not only do you sometimes need to specify the type of your variable as either being a numeric or a string or a character variable, you also sometimes need to talk about the measure. So sometimes you can have either a nominal, which is just a name associated with a variable, ordinal, where it's sort of like small, medium, large, where there is a hierarchy and a direction, or scale, which is, you can think of that as like the SAT. Generally, most of your variables you're going to want you can treat as scale variables unless it is explicitly one of these multi-categorical variables. So let's get back to the assignment. Is each student ID unique? In other words, do we see any duplicates? So there are a couple of ways we can do this. What I tend to do is first, I like to sort my data by ID and just see if there's anything that stands out to me. Usually if you sort by one identifier, you'll start to see duplicates pretty easily. Obviously, there are more formal ways to do this. The easiest way is to do this identify duplicate cases. And what we do here is we choose the variable that we wish to be our primary key, assign whether or not we want to match by cases, and then we choose what we're going to call this sort of duplicate filter. Again, we can either paste. I'm going to do this interactively just because I think it's visually a little bit more entertaining. And what we see here is that there are no zero. And what this primary last variable is it's basically asking, is this the last version of my primary key data? So for instance, if I were to run this again and have a variable, let's call it 101. Let's delete this guy. And basically run the exact same analysis. We'd see we'd have exactly one duplicate case. So that's what that's doing. And let's delete that. Now, the other thing they asked us is to describe the distribution of pretest scores. And there are a few different distributions that I think everyone who does introductory stats should know. I've prepared some slides on that front. There's a uniform distribution, which is sort of what you would get after rolling a die or just picking a random number between 1 and 100. Each number's probability is roughly equal. There are cases where you will encounter uniform distributions. The other distribution you really ought to be familiar with is the normal and all of its approximations thereof. That is sort of your standard bell curve distribution. Lots of things fit that distribution, height, but the basic and important features of the normal distribution is that it's mean centered. Most of the probability is most of its associated probability rests and resides within its mean, and that a lot of data tend to be reasonably approximated by the normal distribution. So those typically are the two distributions that I want you to keep in mind when I ask you these types of questions. So first, let's visualize it. So we're going to go through, we're going to analyze descriptive statistics. All right. Okay, we've got our mean, we've got our mean, our standard deviation, our minimum, maximum, and range. Let's see. All right, and so what we see here is that this is a math assessment. People did very differently. Some students getting like on the range of a C+ to some students not doing very well at all and only getting 20% of the assessment correct. On average, most students failed, but within that failure range, there are a number of abilities that and performances that you might think might require different corrective action. Generally, there are a couple of different ways you could try and visualize this data. I like histograms, but another useful visualization here are box plots. And just thinking through why I might want to use different representations of the data. It might be that I'm looking for different things. Histograms give me a overall picture of the data. Histograms give me an idea of the general shape of the data. So if I were trying to say approximate a distribution or understand what the generating distribution looks like, it's a lot easier for me to see things like the modalities, where the humps tend to be. So we sort of see that there's this hump at around 65. There's this one just at around 30, 31, 32. But if, say, I were more interested in understanding whether or not there were outliers in this data, then I might prefer something more like a box plot. And that has its own utility. Oh, nope. So again, we add the reference variable. And let's take a look at that. What does that tell us? Well, we see actually in this case that there aren't any substantial outliers, that there are no observations outside of our box and whisker plot. So that is good to know. But within that, we see that these tails are very wide and very fat, that it covers a broad range of a test score that we believe to be scaled from 0 to 100. All right, so now we're going to save this data. And as pre-test SPSS. And now we're going to do the same thing with the post-test scores. We're going to go a little bit quicker this time. So what I'm going to do is I'm going to go through, I'm going to import the data again. This time we're looking at post-test. I'm going to click cache data locally. We're going to go through and set the variable to show only one decimal place. Just so you know, that actually is only making things a little bit easier to read. We're not actually losing any data as part of this process. So first thing we're going to do, we're going to see if there are any duplicates. I don't think so, but it's always good to check. Fantastic. We have 0 cases. Now let's take a look at the math post-test score. Descriptive statistics. Again, we want to look at the same variables. And we see here that students did substantially better on the same assessment. But on average, students got around a 75. Remember, the last time we looked at the pre-test scores, that no one even got a 75. So this to suggest that there's been a big increase. Again, the range bottom score we saw was in the 20s. Here, the bottom was around 46. Maximum is now 100. Variances, I actually don't remember what the variance was on this last one, but very much the same, around 15. Okay, so let's see how that affects our answer questions. Well, so now it's asking us to calculate the correlation between student ID and math pre-test scores. Generally, we don't think that there should be a correlation between these two things because your student ID is randomly assigned and typically not a function of anything with regards to your math ability. But we can always check that. And when we do find these sort of odd correlations, it's a very good sign that your data might be doing something you weren't aware of. So for instance, this is really problematic with medical records, that often patient IDs or identifiers can be assigned sequentially. And particularly in the case of outbreaks or patient outcomes or patient assignments, if your ID is in part generated by that sort of information, then it is possible for this information to contain predictive value. And in machine learning, that's called data leakage, but I don't think we're going to have that here. Okay, so looking at the correlation coefficient, we see that there's a very weak negative correlation between student ID and math pretest score. And when we look at the associated significance test, we see that we've got a p-value of 0.139, which is less than the standard threshold we want to use of 0.05. So generally, I would say that there's no relation here. And in general, we also don't have real reasons to think that there should be an association or a mechanism here. So with that, I would say that there's no correlation here. So now we're going to save these data sets. Oh. And then we are going to merge these data. And the way we do that is we are going to go to add variables. If we wanted to add more students, we'd add cases. Then we're going to connect it to a existing SPSS file. And we're going to have to decide on what our merge option is. Generally, there is this option one-to-one based on file order. Unless you are extremely confident, you will almost never want to do that, because all that's going to do is basically take one set of columns and paste them right next to the subsequent set of columns. So if there's one insertion or one deletion of rows, then everything is going to be off. Generally, you're best off using a one-to-one merge based on key values if your observation is an individual. If you want to bring in data from a larger source, say state level information, or there's sort of hierarchical structure like patients within hospitals, then a one-to-many merge might be appropriate. And then we need to select our key. We don't actually care about primary last. And we've got to use the variables tab to get rid of it. So we're going to exclude that. And we're going to do our merge. Fantastic. And generally, in these cases, I think it's almost always worth doing a quick spot check of one or two numbers just to make sure that it's consistent with your own sense. We're going to skip that here, but it's something that I still do, and regularly. It's one of the most important aspects of data engineering, is just to do a quick smell test of your own work. Now, moving on to the remaining parts of the exercise, we have successfully merged the data. Now what we're going to do is we're going to calculate the pre and post-test correlation. We're going to go down to bivariate correlation. And what we're going to do is add both of those variables. Okay, and here we see that there is very strong correlation between your pre-test and post-test performance. That what a correlation coefficient is it tells me the co-movement between the two variables, in particular, how closely they move in the same direction. And what this tells me is that if I know your pre-test score, I can very easily predict your post-test score with a high degree of predictive accuracy. This is very close to 1, meaning that it's an almost perfectly linear relationship. But as we learn through playing the guess the correlation game, that generally as these correlations shrink, it becomes much harder to tell how close these patterns map. So we are now on part C. There are a number of ways you might want to look at how to visualize these data. The one that I tend to default to when you have small data and not a ton of points is a scatter plot. It's very easy to see these visualizations. So what we're going to do is we're going to go to our chart builder. We're going to go down to scatter dot plot. We're going to do a simple scatter line with a fit line. We're going to put math POTUS on the y-axis. And now let's take a look. And we can see that just like we said, there's a very close to linear relationship. This line is what's called the line of best fit. It's a regression line. And we are just trying to put a line through it that minimizes the variance in our predictive performance. And here we have our R-squared coefficient, which is the square of the correlation coefficient. And R-squared tends to be a more preferred measure of fit and the explanatory power of a regression. Depending on the circumstances, you might want high R-squared, saying that you are explaining most of the features of your model. But if you're doing things like causal inference, this R-squared component really isn't that important. Now we're going to make that pre to post variable. So we're going to go through data, and there are a couple of ways we can do this. But the easiest is to go down and compute that ourselves. There are a number of other functions we could use. I'm going to call this a gain score. And then what we're going to do is we're going to run a t-test to compare the values of pre-test and post-test scores. And the way we're going to do that is with a paired t-test. And we're going to have our math pretest and our math post-test. And what we see here is that on average, students pre-test scores were on average 29 points lower than their post-test scores. Let's frame it the other way. And we see that we've got a high t statistic and the significance is less than 0.05. So this is a very statistically significant result. Let's do it the other way because I think it's a little bit more intuitive. And here, when we flip the variables, we see we have the exact same results. The only difference is the signs are different. That the mean difference is 29 points. That the t statistic is 67, is a positive 67, and the significance is still 0. And this is because we're doing a symmetric statistical test. There are one-way statistical tests where we're just saying if things are greater or less than a threshold value, but generally you are going to want to prefer a two-sided t-test unless you have strong reasons to think otherwise. So now we're going to look at our gain score variable and compute a histogram. Oh, no, I did not grab the right variable, did I? And this is why point and click is a little bit dangerous, that sometimes your defaults are already set for you and you might use them when you don't quite fully realize them. Here we see that largely everyone gained and benefited from this on the post test. That the worst that a person did was they gained about 15, whereas some individuals gained by nearly 40 points, which is really quite impressive and much larger than what you typically would see in any educational intervention. That typically, if you go back to the standard deviation, you sort of see that the standard deviation is 4 in this case. Generally, most outcomes or interventions that an educational assessment provides will maybe create a 1 or 2 standard deviation increase. So maybe 8 to 10 points is sort of like the best you could hope for. Here, this is a ridiculous gain, which makes me start to think maybe this is just an artifact of how the pre-test versus the post-test could be constructed. That's something to keep in mind. So that's something we can't really even test. But now we're gonna, what we're going to do is we're gonna compare and see if our one sample t-test, if our gain score is significantly different than 0. And the answer is yes. We see that the significance value is 0. The t-statistic is 67.014, and that the mean difference is around 29 points. And what I want you to take away is that in all 3 of these cases, no matter how we did the statistical test, we got the same results. This isn't always going to be the case, but generally, the big takeaway is that these are all a form of regression, and that all these forms of regression are all very similar to one another. Let's see. I think this is a good stopping point. There's one last thing that I want to show you, and that is how we can do the same analysis as linear regression. And so what we can do is we can look at our math post-test score. We can look at our math pre-test score. And so what we're doing is we're modeling our outcomes as our math post-test score as a function of your pre-test score plus an intercept. And we're going to do that. And what I want you to see is that we have our unstandardized coefficient, which is exactly our correlation coefficient, or approximately our correlation coefficient. We've got our correlation coefficient here, that's R. We've got our R squared, which is the scatter plot. And we've got this ANOVA, which is another way of representing a statistical significance analysis. Yeah, so I think that's a good place to leave things. Thank you so much. I'm looking forward to seeing you all next week. Bye.